Hello and good evening. My name is Masume Jahani. I am Associate Professor in Engineering Management at University of York. My research focuses on application of AI in engineering field to improve sustainability. So let me welcome to everyone to the winter webinar series, particularly our offer holder. So for a long time, humans have been designing and constructing a robot for familiar environment. But have you ever thought, what if, because of our lack of knowledge about unfamiliar environment, the robot we as a human created for this environment are not operating efficiently? So the main question is, can robot design and produce other robots? In this webinar, Dr. Edgar is going to answer this question and even more. So you're going to find out. Let's just, talk about Dr. Edgar. I can see Dr. Edgar just join us. Dr. Edgar Buchanan Beruman earned his PhD in 2019 from University of York. After finishing his PhD, he worked as an associate research associate on the project, which is the title of tonight's talk, Autonomous Robotic Evolution. And now currently Edgar is a research fellow on the Reimaging Engineering Design project. So let me stop talking and hand over to Edgar to tell you more about this topic, the Autonomous Robot Evolution project. Over to you, Edgar.
Hello, everyone. Thanks for having me here. Before I go into any detail about this project, I would like to give a little bit of context about what's the objective, the long-term vision of this project, and how we plan to take small steps towards this target. Right, let's start. So this project is it focuses on the disruptive robotic technology where robots are created, reproduce, evolve in real time and real space. The long-term vision is technology. Let's skip that and let's go to the 1969. Back then, there was this space race going on between two countries, the US and the USR, or Russia nowadays. And they both were competing to see which country was the first country to send a person and land on the moon. And spoilers, but US was the first one to reach the moon. And after that, space exploration became slow and there was not much going on. But it was not until recently that there is this excitement again about the space exploration, and now different countries and different companies are investing in space exploration. And now, more than ever, it feels like we are closer to send people to Mars. So, are we living a second space age? Well, I cannot answer that, but I could say that yes. But there are three main issues right now with current space exploration, in my opinion. The first one is that it's very expensive. The second one is that it's not eco-friendly. And also, we don't have a full grasp about how we know everything about Earth. Well, not everything, but we don't know about landscapes, for example, Mars and Jupiter. And how, if we send a robot, how is this robot gonna interact with this environment? But I'm gonna go into more detail of each one of these issues. Let's start with how expensive it is. Right, so this graph shows how much it costs to send 1 kilogram of anything to space across different years, across different decades. But let's look at the beginning. In the 60s, between the 60s and 70s, the price of sending 1 kilo of anything, it was somewhere between $3,000 and $12,000. over time, the price has dropped, and now it's between, let's say, $800, but that's still expensive. That's 1 kilo of anything. So if we want to send provisions or food to people, it's gonna be very expensive, and we need to do it quite often. So we need to make multiple trips back and forth. So it's still very expensive. The price is dropping, but still expensive. The second one, that is not very eco-friendly. So this graph compares how much CO2 a rocket produces and how much an aircraft CO2 produces for the same, how many miles you can travel with the same production of CO2. So let's look at the first one. So if you want to travel 100 miles in a rocket, it will produce more than 1,000 kilograms of CO2. For the same amount of CO2, you can travel close to 7,000 miles in a conventional business class aircraft. So if we compare both, rockets are definitely produce more CO2 than conventional aircrafts. And this is not good if we think about the long term about our planet and that we want to reduce emissions, CO2 emissions. The last one, that we don't have full grasp about unknown environments. This is a Mars rover that it was developed in the middle of the 2000s. And it was manufactured and produced here. It was designed by engineers and scientists here on Earth. And well, scientists made a lot of assumptions about the surface of Mars, and they designed this robot with those assumptions. But as soon as they sent this robot to Mars, after a period of time, the robot got stuck with sand and the robot was not able to move. And this is serious because this project was very expensive. It was very expensive to send this Mars rover to Mars. So what the engineers did here on Earth was to try to replicate the same environment of Mars here on Earth in order to find a way to make the robot move again. But unfortunately, they were not able to do it. This is not a quote from that robot, but I like this quote from a different Mars robot. Anyways, so that project had to stop, and that's because of the assumptions of the engineers made, because we don't fully understand how the surface of Mars is. There we go. So we have 3 challenges. What can we do about it? Well, something that we can do is that in traditional space exploration, if we want to create a settlement in a different planet, what we will do is to send an aircraft to, let's say, Mars with people and equipment. And these people and equipment are going to start creating facilities for the people. And then, but at some point, we need to send that aircraft back because we need to restock about provisions and maybe the people need to rest. And this process repeats multiple times until we are happy with the settlement that we have on a different planet. But every time that we send back and forth this this rocket, we produce CO2, it's expensive, and also it's gonna take a long time to do this. So what we can do instead is we can send a single rocket with equipment and personnel, but this time, instead of creating the facilities, we create something that we are gonna call the robot fabricator. This robot fabricator, what it's gonna do next is that it's gonna use the same resources of that specific planet to create smaller robots. And these robots are gonna help to create the facilities that we need. And since these robots are operating, and since the robot fabricator is operating on this planet, they know all the environments and they can design robots that can work very well in this planet. And if we need more facilities, the robot fabricator uses more resources from the planet and construct more facilities until we are happy with those facilities and we can send people to live there. This is the Autonomous Robot Evolution project. Like I was introduced before, my name is Edgar Buchanan, a research fellow, and this project takes the first baby steps towards this direction. And I'm gonna describe to you our progress that we did so far. Right, so a question that I have is, and that we had in this project is, could a robot design and produce other robots? And hopefully by the end of this presentation, we're gonna have an answer. The robot that I'm gonna use as an example for this presentation is this one. The official name of this robot is called 56, but for this specific presentation, it's gonna be referred as Bob. And we are gonna see how Bob was created from the very beginning and how it was autonomously fabricated and how it's able to perform its mission. Right, but what is the mission of Bob that needs to do? Well, basically, what Bob needs to do is to move from one end of an environment and reach a beacon on the other side of the environment. But the problem with this environment, what makes it challenging, is there are these two sets of ridges in the middle. So a robot with wheels is not able to reach the beacon. So it needs more than wheels to reach the beacon. It needs some sort of legs to do it. And the way that we evaluate this robot is according to how close it gets to the beacon. And this robot went through this process where the robot was firstly simulated, and then it was autonomously fabricated, and then we have the final product. I'm gonna go through each stage in more detail. In the first stage, the robot is simulated in a computer because there are many advantages of this. It's very quick to simulate a robot. It's very cheap because we don't have to manufacture it, and it's fast to do it. In order to design this robot, we use an AI that takes inspiration from nature, not from this specific nature, but from this. In this case, from the natural selection. I'm gonna give you a little bit of explanation how the AI designed these robots and how it takes inspiration from that natural selection. In the 1800s, Charles Darwin went to the Galapagos Islands and he found something very amazing in these islands. He found that a group of birds of the same family, of the same species, they had big, chunky beaks. And these birds use these chunky beaks to eat seeds so they could break through the shell and eat what is inside. But he found that there was another group of birds that they had these smaller beaks. And these birds use these smaller beaks to go through the gaps of trees to get these insects that they were hidden inside. So basically what happened is that each bird adapted to their own environment. In this case, they adapted to the food that they needed to eat. If they wanted to eat seeds, they needed to grow bigger pigs. If they wanted to eat the bugs, they needed smaller pigs. So the natural selection was able to find a way for these birds to survive. So we want something similar in robotics. We want the robots to survive their environments so they can adapt and they perform well. Now I'm gonna give you a small example about how does this takes place. It's a very high level example, but imagine that you have a group of robots. In this case, there are 10 robots. Each of these 10 robots is represented by a different color. What we do is that in simulation, we evaluate each of these robots and we give them a score or a mark, and we say, oh, how close you got to the beacon. And the best robots, they got a 10. The second best, it got a 9, and so forth. Which one? And the worst one, it got a 1. So what this algorithm does, it takes the 2 best ones and takes them as parents, and it combines the genes of both to create what we call a new population of robots. And this new population of robots have similar characteristics or features of the parents. For example, I'm illustrating this as a colors. This population of robots has in the orange range. And we repeat this process again. We evaluate the 10 robots and we give them a score of how close they go to the beacon. And we rank them and say, oh, you did very well, you get a 10. You didn't do so good, so you got a 1. And we select the 2 best ones and we combine the genes and we generate a new population. And slowly over time, we produce better and better robots in this way. The AI, this is what it's doing in a nutshell. Now I'm gonna show you how it looks like in simulation. So what the things that I'm showing here is that the first layer is the grandparents, and how the grandparents, they were not very efficient in doing their job of reaching the beacon on the right-hand side. But slowly over time, as the parents and the children are born, they are born with new characteristics that they make it better to solve the environment. For example, you start to see that these 2 parents, they have similar characteristics as Bob, and Bob is a child, by the way. Bob, if you remember the robot early on in this presentation. And now Bob has the body that can solve this task, but maybe it doesn't have the brain to solve it, so we need to do something about it. A robot, like I was saying, is a body and a brain. We have the body, but what about the brain? The robot needs to learn to do this task, and now Bob needs to go through a learning process where it learns to perform this task. And this is shown in this video. The top left video shows an early stage in the learning process where the robot doesn't know what to do and it just stays on the spot. But as the learning process goes through, it becomes smarter and smarter. And the robot on the bottom right is the most smarter one, and it's able to reach the target. And we do this for every single robot. It struggles there, but it's able to reach it. There we go. Right, so we have the body, we have the brain in simulation. Now what we need to do is to translate it. Oh, here's a video in more detail, how it shows the process of the robot reaching the target. I'm gonna fast forward it. And here we go. So yes, we have the robot in simulation. The next step that we need to do is to construct this robot, to fabricate it. If we're gonna have a facility like this in a different planet, we need to make it autonomous so a robot fabricator is able to fabricate these smaller robots. And here is our approach of the robot fabricator. This is our robot fabricator, also known as RoboFab. And I'm gonna describe what are the main components of this robot fabricator. In the middle, there is a robot arm. The robot arm takes the different components and puts them together and as a robot. We have 2 3D printers, which 3D print what we call the skeleton of robot, the green bit that surrounds it. And this green bit can take any shape. And this shape is selected through the algorithms that I was explaining, is selected by the AI through the natural selection process. There is a component bank where the robot arm can take all the pieces. For example, it can have a wheel, it can have a leg, it can have a sensor, and in the robot arm attaches these components to the skeleton of the robot. Here in the middle is something that we call the assembly fixture. And what it does, it holds the robot tight. There are 4 electromagnets that hold the robot, and this rotates, so it grants access to the robot arm from different directions, so the robot arm can attach the different components. And now I'm gonna show you a video of an assembly. This is, I believe, 8 times speed. So what the robot does first is to grab that sensor, connects it to the skeleton, and then it grabs that cable, which is a spring cable, and connects it to the what we call the head of the robot. In the head, there is a computer. In this case, it's a Raspberry Pi, and the process repeats again for every single component. The entire process takes roughly 7 minutes. I mean, the assembly process. The 3D print part is the longest one. It takes roughly like 3 or 4 hours. That's why we have 2 3D printers, so we can parallelize the process and make it more efficient. And this is something that we would like to optimize in the future, how we can reduce the printing time, because it's quite long compared to the assembly process, which takes 7 minutes. And the reason that we use retractable cables was because they get out of the way of the robot, because in the past we were using long cables, and sometimes when the robot moved, they were getting in the way. And there we have it. That's how we autonomously fabricate robots. Right, so we are going through the last stage of the process. And now that we have autonomously fabricated a robot and we have our physical robot, not in simulation, what we need to do next is to evaluate this robot. And what we do is that we replicate the same environment in simulation, in reality, just to see if it's gonna work. We put exactly the same brain in the same body, same environment, and the expectation is that gonna work. And my question will be, do you think it's gonna work? Let's find out. Right, something went wrong, right? Let's compare the simulation and the hardware or the physical one once again, just to see the differences. The one at the top is a simulation, the one at the bottom is the physical one. Right, the one in simulation is able to reach the target, whereas the physical one wasn't able to reach it. Why is this the case? If it's the same body and if it's the same brain, why it didn't work? Well, do you remember when I was mentioning early on that scientists and engineers, when they were designing the Mars rover, they made assumptions about Mars? It happened the same for us. When we are working with simulations, in order to make it fast and efficient, we make a lot of assumptions. One of the assumptions is, for example, the friction between the floor and the wheels and the legs. The friction is not exactly the same. So, for example, it's more slippery in simulation. Another reason could be that the joints, they don't move in reality as accurate as in simulation. Also, when the robot interacts with the bridges, it's not the same interaction in the simulation than in the physical one. So we have all these small differences that slowly accumulate and they affect the performance of the robot. This is called reality gap. And the reality gap is the difference between simulation and the physical robot. What can we do about it? So we have this problem that the robot is not doing the same thing as the physical robot as the simulation one. Well, we can make more accurate simulations. But the problem with this is that there are two problems. It becomes more expensive and the simulations become slower because you have to simulate, for example, the contact of the robot with the ground, and that's very computationally expensive. And the main reason that we were using simulations at the first place is because it's very fast. And if we are going to make it slower, it makes it more difficult to evaluate like many robots because we were talking about like 10 or more robots at the time. So we want to do it quickly. So this is not the best approach. What about we drop the idea of simulation and we do everything with a physical robot in hardware? In this way, we remove the reality gap altogether. But we come across a new problem. And the new problem is that we need to fabricate every single of these robots. And this becomes very expensive and time consuming. And this is because we need to 3D print every single robot and we need to autonomously fabricate every single robot. And the evaluation of one robot in simulation, it takes, let's say, 1 second, whereas in hardware, it takes 1 minute. But for example, if we need the robot to learn, we need to do that 100 times. And that's 100 minutes. And if you start to accumulate all this time, it's going to affect evolution at some point. What about learning in the robot? So we put the same copy of the brain of the simulation in the hardware one, but it didn't work because of all of these assumptions. What if the robot learns in the physical environment and it adjusts the brain so it works in this new environment? It should be more efficient. Let's have a look. This is a video of a robot learning in the physical environment. Similar learning as a simulation, but now in the physical environment. So now it's adapting its brain so it works with this new physical environment. And slowly, over time, the robot becomes better and better until the robot is able to reach the target. This is one of the best behaviors of the robot. And now it's doing the similar thing as the one in simulation. And there we have it. I went through the process of describing how Bob was created in simulation, how it was autonomously fabricated, and how now it performs well, relatively well in hardware. But this is not the end. This is just the beginning. Because Bob is a good robot, but it could become better. For example, it has too many wheels and it has two legs. So what we do is that we take the performance of Bob and we send it back to the simulation and we refine it. We evolve more robots like Bob. Once we are happy what we have in simulation, we take the best robot in simulation and we autonomously fabricate it. And we have this robot that is called Tim, and this is a child of Bob. And slowly, over time, we are creating better and better robots that they work for this specific environment. We haven't gone through many iterations. This is where we stop, but we are aiming to produce more generations of robots, of physical robots. Right. So we are coming to the end of this presentation. Just to remind you of the stuff that I went through this presentation is that we use an AI that takes inspiration from the natural selection to design the body and the brain of the robots. We do this first in simulation, and then the robots get autonomous. Once we are happy with the design, the robots get fabricated, autonomously fabricated, and then we evaluate the robots in hardware because they are gonna have different performance because of their reality gap. Then the robot needs to learn this new environment, how to operate in this new environment. And what's the point of everything? Because at some point we want to have a similar facility in a different planet that can operate and that we can create robots that are adjusted for those type of environments. And yeah, to conclude, could a robot design and produce other robots? Yes, maybe. We are getting very close, and that's the point. And I just want to thank our team. This is a UKRA EPSRC project across 3 different universities: Napier University in Edinburgh, University of West England, and Bristol, and the University of York. And that's everything for my side. Thank you very much for listening.
Thank you very much, Edgar. I should say it was very interesting indeed. I really enjoyed the demonstration of the simulation you shared with us. So now is question time. So let me see if we have any questions. So you can help me. Of course, that is reflect to what you presented. So I think you are the best person to answer that. I am going, since I am working with multi-screen, sorry if I can't just, look at that one. So I need to move to that screen and see what question we have. Yes. Okay. Let me start the question. Um, One participant just ask, am I right if I think that is a very long-term goal for robots to refine resource on Mars, then assemble new robot from scratch?
That's a good question. Yes, it's a long term, but it's not as long as we think as we are. And the reason that I'm saying this is because at one conference that I went, I met a researcher who is doing research about how you can use materials. He was thinking about on the moon. How can you use moon materials you can find in the moon to 3D print parts of robots? In this case, what he was doing is 3D print motors of the robots. So there are people that are working towards this direction, that they can mine the resources of the planet, and then you can use those resources to 3D print those robots. But yeah, it's a long-term goal to do this.
Thank you very much, Edgar. There is another question, just asking, what is the main limitation on further development right now?
Yeah. Oh, there are a few limitations in this. One that I mentioned in this presentation is a 3D printing part that is very slow. The second one is right now we have what we call the skeleton that can be 3D printed, but we have other components that were designed by us, like the wheels, like the brain, like the legs. These were humanly designed. But what we want to do in the long term is we want to let the AI to design these components. But there are challenges with this. One of the challenges is that to design and to produce the electronics, that's very, very hard. You cannot just 3D print the electronics. There's some progress on this. For example, there is this conductive 3D filament that you can use, and you can have electricity flow through this filament. But it's in early stages, this filament. The conductivity is not really good as it is right now, but hopefully as research continues, the conductivity is going to increase. And this is going to help us not only design the electronics, but also, for example, if you remember, we are using spring cables, but what if we could 3D print this with this conductive material? That would be really cool, but the technology is not there quite yet. So we had to use these springy cables, but that would be really cool to 3D print these conductive materials.
Okay, thank you
Yeah.
very much, Edgar. And there are actually, everyone just, thank you for such an interesting talk. And we have another question. We often ask nature versus nurture. What balance did you find is needed between design evolution and online learning?
Hmm.
Very
Yeah,
deep question indeed.
yeah, this is a very good question. I think online learning is very important. That's a lesson that we learn from this project. We can let evolution of the AI to design the bodies, but due to the reality gap that was mentioned in the presentation, there has to be some online learning when you are deploying your physical robots. So they have to learn about this new environment and they need to operate. So what we can do is that we can start a robot, a physical robot, with some sort of controller or brain that it kind of works, but this robot definitely needs fine-tuning with online learning. So we need to find the appropriate balance that we give it a good starting point from the brain, and it doesn't start from scratch, because otherwise, if we start with a blank brain, it's going to take ages for online learning to do something. So we need to find the right balance. And what we expect from this project is that the simulation gives enough information for the brain, from the starting brain, so we can do the online learning and we don't do it from scratch. So the robot knows some stuff, how to do some stuff. So it needs only to refine those actions so it can operate in this new environment.
Thank you very much, Edgar. There is a long question. I think you already just answered the first part, but which back to limitation in general. But the second part is asking, is there any consideration on speed of robot or any other parameter to help align goal than just reaching the target?
Yeah. For this specific scenario, for this specific mission of the robot that I was describing in the presentation, it was just distance, how close you got to the beacon. But that metric or that performance can change, like this person suggested. We can measure other stuff like speed, like stability, how the robot moves in terms of stability. Speed is very important. We are not considering it right now, but it could be very beneficial because we want the robots to perform the task as quick as we can. For example, in the videos that I was showing you, it was not very quick. Maybe we can introduce this speed metric to make it even better. But no, we are not limited in terms of the metrics that we use, and we can use other metrics besides of distance to improve the robots. This was just the starting step that we took.
Okay, thank you very much. Another participant, and just thank you for the great talk, and also ask, could you please explain on the simulation stage? And how much physics did you retain in your simulation software? And also very technical one, how do you instruct the robot to seek out the beacon? Is it just trying to minimize the distance between itself and the beacon? So if you can briefly explain about some level of detail, that would be great for this participant as well.
Yeah, no problem. The simulator that we're using is called Coppelia Sim, and is quite widely used. In terms of the physics engine, we're using a physics engine called Bullet, which is also quite widely used, but it's quite, I will say, granular, and it doesn't give you enough definition of how the robot interacts with the environment. Just to give you one example is that I was talking about the friction between the wheels and the floor, but this physics engine simulates it by using one coefficient only, and it simulates it like a point contact. And in reality, this is not the case because friction is more complex than that. It's more complex than that single point. It's more surface to surface. And according to the amount of surface, there is more friction, blah, blah, blah. But all this kind of stuff is doing the simulation. This is a very high level description of the simulator that we are using. In terms of how the robot knows where the beacon is, the beacon, I didn't give those details, but what the beacon does is it emits infrared light, and the robot has an infrared sensor, so it can see where the infrared light is coming from. So the robot, it turns itself, it aligns itself towards the beacon, and it starts to move towards that direction. So yeah, that's it.
Yeah, thank you very much, Edgar. Actually, the question is coming, so perhaps we can provide a brief answer in order to manage, address all of the question. The next question is, how do you predict how material will behave on Mars?
Oh, that's the point.
Yeah.
We want to have this facility in a different planet. So the AI So when you are deploying your robots in a different planet, they are doing their stuff and that kind of stuff, and you are measuring their performance. And the AI takes this information from this performance of the robot in this other planet, and then it changes itself and it adjusts its information. For example, going back to the previous question about the simulator. So let's imagine that you have your friction coefficients, you model your friction in a way, and you say, oh, my friction coefficient is 2, for say something. But after you deploy your robots and you notice, oh, this friction coefficient is not accurate enough. Maybe the AI learns to change this and say, oh, what if number 2 is number 3 or number 1? And in this way, slowly over time, the simulation becomes better and this reality gap becomes narrow and narrow and narrow over time because the AI is learning about this environment and it's adjusting its parameters so it matches better the reality. And in this way, we don't need to learn about the environment. The AI learns about that environment and it doesn't need to make the assumptions that we make.
Okay, thank you very much. We have actually a very interesting question regarding recycling. Has been any consideration on recycling parts from robot which have become damaged to reuse the part autonomously?
Right. So yes, we had this on mind when we were working in this project. The different components, the wheels, the legs, the sensors, the brain, they can be reused anytime. If you are not happy with the robot, you just take the components and put them in a different robot. Easy peasy. In terms of the plastic that we're 3D printing, there has been progress and there is 3D filament recyclable. What happens is that you destroy the plastic and you make it pebbles again, and you melt it and you make it a filament again that you can reuse. So you can reuse the components of the robot and you can recycle the plastic that you use by breaking it again into pieces, into small pebbles that you melt and make it a filament again.
Thank you. Very good answer indeed. There is another one. Excellent presentation. Would you consider producing 3D metal parts?
Oh, we thought about it, but again, it's one of those that the technology is not there yet. So we had to stick with plastic. And the reason that the technology is not there is if you want to 3D printers that print metal exist and they're using in industry, but they require high maintenance. They require health and safety training, like very high safe health, because they use very high temperature to melt the metal. And for example, the 3D printer that I was showing you in the videos, it's open. So the robot arm can go and grab the skeleton or whatever. But this is not the case for metallic 3D printers. They need to be enclosed in order to keep it safe. And also they're very expensive. The materials are expensive. The energy that they take to 3D print the metallic parts is expensive. So no, we decided to go for plastic for now because yeah, the technology is not quite there for this specific application.
Okay, thank you very much. And another question asking about how are the instruction for the fabrication of Bob and Tim transfer from the simulation to the robot, which creates Bob and Tim? Is it fully autonomous or is there human intervention involved?
No, I will say it's fully autonomous. This aspect, I'm gonna just mentioning the things that are not autonomous. In terms of the brain, that's autonomous because it's basically, how can I describe it? It's just like a text file that describes how the brain is configured, and we send this text file to the brain of the robot, and the brain of the robot reads this text file and does its job. The thing that is not automated is that if you remember, the robot is held in assembly fixture and all the components are put together there and it rotates and everything. but there's nothing to take the robot away from there. So we need to grab the robot from there and put it into an environment, and the robot moves in the environment and does its stuff. Sometimes we need to place the robot again at a certain location, so the robot does the same task over and over again. This is not has been automated, and it can be automated, but we didn't do it in this project. But in terms of transferring the knowledge of the brain in simulation to the brain of the physical robot, that's been automated.
Okay, thank you very much. And one of our participants just ask, is this I assume refer to project, is this being done elsewhere?
At this level, I will say no.
Okay.
There's only one project that comes to my head that did similar stuff. In this project, they had a robot arm, and they used similar algorithms to create the robots. But these robots were small cubes, and I like it because what it does is that the robot arm took one cube, and no, the first thing that the robot arm did was to put glue on one of the cubes, and then we grab a second cube and put that cube where the glue was put. And these robots didn't have any sensors, wheels, or legs, or whatever. The way that they moved was through vibrations, so they were very minimalistic. That's the only one that I know so far.
Okay, brilliant. So another question asking about the component, because apparently the component is collecting from 3D printing. Do you plan to just manufacture everything in future?
Yes, that would be the dream. There are some challenges, like I was mentioning early, like 3D printing the electronics. The technology is not quite there yet, but that would be the dream, so we could 3D print everything.
Okay, thank you very much. Have you considered issue with 3D printing on Mars or the Moon due to differences in gravity?
Yeah, this is a question that I haven't thought before. Yes, there are some limitations, and needs to be considered. For example, the first one that comes to my head is that we wouldn't 3D print plastic because this will melt right away. But in terms of the different gravity, in terms of the soil conditions, this is something that needs to be considered very carefully if we want to operate 3D printers. Mainly the gravity, because since the 3D printer relies of like the drop of filament, that's very important. But yeah, this is important to consider the design, how these 3D printers are gonna look like for this planet. That's exciting.
And two interesting questions. One, eventually, do you believe this will be used on a larger scale or mass production than Mars, using self-creating robots to map out the universe?
That would be really cool. I hope
Yeah,
so.
it's like a future movie and science movie, science fiction movie.
Yeah.
Okay, so if you were successful in this project and created a civilization on Mars, would it be have the manpower to many enough transport to get there?
I guess hmm, that's more logistics than anything.
Yes, I think it's more about logistic and resource management in
Yeah.
order to achieve the goal for that mission. So, a very good question, but it involves supply chain management, logistic, and the resource we need to allocate for achieving that goal. So, would you be intending to use a fleet of Earth-made robots to collect resources?
No, what we envision is that they are not Earth-made, and they are made in the location that they are operating. Well,
Okay.
these specific robots that are going to collect the resources.
Are there a limitation or any restriction in place on the artificial intelligence or AI to stop the learning and designing from becoming dangerous?
Yeah, I like these kind of questions. Yes, we have thought about this. The way that we envision it is that this facility is gonna operate with they often call it like a heartbeat signal. There's gonna be a signal being sent from Earth to this facility in a different planet or location. And if at some point we humans believe that this is getting out of control, we can stop sending this heartbeat signal. And when the facility stops receiving this signal, everything stops and all the power shuts down and everything. It's important to have these safety measures. I don't know if it can happen. It might, but it's important to have these safety measures in the long-term vision.
Okay, I think you already answered this question. 50 years in the future, what is a stop an AI machine making a dangerous robot? You already just, answered. So was there any physical feature that you were pleasantly surprised for the AI to develop, or which was an unexpected development of the natural selection?
Uh, what's interesting about using algorithms of natural selection, it produces a lot of, I'm gonna use the word like weird, wacky stuff that you don't expect. And that's good, but sometimes it's bad. For example, something that we discovered when we were working in this project is that the assumptions that we made in simulation, sometimes the AI exploited those. For example, let's say if the friction is very low in your simulation, the natural selection is gonna create robots with only wheels. And at the beginning you are like, well, why is that happening? But after you do reasoning, you discover that that's the reason. But yeah, natural selection likes to exploit all of this stuff so it can produce good robots. But sometimes it's good because it creates robots out of the box that humans wouldn't have been able to design. And that's why we are using natural selection, because it's very creative. But sometimes it can exploit these small things in simulation and things that we don't want that to do.
Okay, thank you very much. There are a few questions left, but it's similar to what you answered. But the last one, I think it is very important to answer, is especially for our offer holder, is how could a university undergraduate student get involved in a project like that?
Yes. What we do is that every year we advertise projects for undergrads and for MEng, and any student can apply and can get in touch with us, and yeah, they can work with us. But yeah, every year we advertise positions to work in this project for undergrads.
Thank you very much, Edgar. Thank you very much, everyone. We need to wrap up. It's over 7:30 in the evening now. I really enjoyed the talk, and I am sure all of audience enjoy as well because of all of the question and thank you messages they sent it to you, Edgar. But
Thank
we need to wrap
you.
it up. Yeah, thank you again, Edgar. And thank you very much, everyone. And I hope you have a fantastic night tonight. Thank you. Bye.